Good afternoon, everybody. I hope you had a successful day yesterday and you were able to get a hold of all of the materials you needed for the work. And you were able to access the YouTube video. Just a couple of issues with the technology here. Some of you had indicated to me that the YouTube video, if you were listening to the video while you were watching it using headphones, or if you were listening with a stereo output, that it only had sound in the left channel. So I think I figured out what the problem is and how to fix that. Hopefully it won't happen in future videos. There was another issue though that was a bigger issue, that some of you had problems either printing things out, or I got an email from a couple of people saying when they were looking at their note package they were missing some questions. This is an issue with Google Drive and shared folders and Google Chrome. When you double click on a file when you're in your Google Drive through the Google Chrome web browser, Google Chrome, the browser, takes control and it decides to open the PDF file. And Google Chrome is not designed for PDF files. And as a result, it doesn't do a very good job of deciphering them. So sometimes you get pieces that are missing or pieces that are garbled, and it gets even worse, or it can get even worse when you go to print things. So when you have documents that you want to view that are in PDF form, or they are documents that are in PDF form that you want to print, it's always a good idea to download the file or save the file to your desktop and then open it with a dedicated PDF reading file like Adobe Acrobat or Foxit PDF Reader. There's lots of them out there. Anyway, today we're going to be moving on. Welcome back again. This is Math 30.01, solving quadratic trigonometric equations. And this will be the second time I've taught this lesson because I just finished teaching it, but I forgot to turn my mic on. So I'm just looking at my microphone right now and making sure that it is on this time. This is on page 2 of your handout, part 1 of the rest of the story. And before we actually get to equations that we're going to be solving today, we're going to back up and we're going to solve some equations that range in difficulty from anything that a grade 5 or 6 student could solve to something that would require Math 20 level skills. So when I take a look at, I'm going to rewrite this so I have just a little bit of extra room. I'm going to rewrite this so I just have a little bit of extra room. I have 2x minus 1 is equal to 0. And I know that most of us look at that and go, well, that means x is equal to 1/2. And that's true. But the procedure that you use in order to find out what x is equal to is you start off by adding 1 to both sides. That gives you a new equation which says 2x is equal to 1. And then you can divide both sides by 2. And that leads you to the statement that x is equal to 1/2 because these two 2's cancel. Very, very simple equation to solve. When we take a look at the middle equation, which is b, it's even simpler. All you need to do here is subtract 1 from both sides. And you know what? This is so simple, in fact, I'm not even sure that you would, even on a diploma exam, even though you don't have to worry about that, I'm not even sure you would need to write that you're subtracting 1 from both sides. So we have two solutions to these two equations. The solution to the first equation is x equals negative 1/2, and the solution to the second equation, let me repeat that. The solution to the first equation is x equals positive 1/2, and the solution to the second is x equals negative 1. Now, how do we go about solving an equation like 2x squared plus x minus 1 equals 0? You go from, and this is a common theme in high school math, in fact in math all over the place, you want to take a math problem that is at a higher level and turn it into a math problem that is a lower level. So right now, this is an equation that I would describe as being a Math 20 equation. But in Math 10 and 20, you learn that this 2x squared plus x minus 1 can be factored. And I'm not going to spend a bunch of time in this video reviewing factoring. I'm going to talk my way through this, but I'm not going to write down a lot of details. This is going to factor into two binomials, and the first term in each binomial must be, it has to be 2 and 1 for the simple fact that this multiplied by this when you FOIL it out has to give you 2x squared. And we need an x in each term because when we FOIL this out, we're going to need a middle term that has a linear property. In other words, we need x's. When I take a look at the remaining pieces that I need to factor here, and again, I'm spending maybe even more time than I need to. We need a 1 here and a 1 here. And the reason is that 1 times the 1 has to give us this 1 up top. And I know that one of those 1's must be positive and one of those 1's must be negative. And now we're going to figure out which is which. If I were to FOIL this out, the 2x multiplied by the x gives me the 2x squared. So I know that that's correct. The 1 multiplied by the 1 gives me the 1. So I know that's correct. All I need to do now is look at my outer and inner. My outer is 2x times 1, which is 2x. My inner is 1 times x, which is x. And I need to combine these two terms to get positive 1x in my quadratic. The only way that's going to happen is if the 2x is positive and the 1x is negative. And then you reverse engineer this. How can you get negative 1x? By putting a negative in front of the 1 that's in the first set of brackets, and that makes the other one positive. Now, what we have done is we have gone from this equation, which is a Math 20 equation, to this equation, which is actually a Math 6 equation. Not yet, but it's about to turn into a Math 6 equation. Because if you have, and I'm going to get rid of this because I don't think, quite frankly, many of us needed even to write that. When you have A multiplied by B equaling 0, the only way that can happen is if either of those two factors are 0. So 2x minus 1 equals 0, or x plus 1 equals 0. And this is what you learned in Math 20. But again, quite frankly, solving these two equations is something I would expect from a grade 6 student. At this level, it's like taking candy away from a weak, tired baby. It's pretty easy to do. And you will notice something, that each of these two equations are the two equations I had in A and B. So we don't even need to do any more work. The solution here is x equals 1/2, and the solution here is x equals -1. What's the lesson here? The lesson is that you take a quadratic expression that's in an equation equal to 0, and you factor it so that you can solve linear equations equal to 0. It's much simpler. So now let's take a look at the first example at this level. We are asked, I guess before I do that, when we solve trigonometric equations that are quadratic, and I'm going to show you what that looks like in a second, you use the same idea. So yesterday we reviewed how to solve trigonometric equations like this. I think it was sine of theta equals -0.8. And this is considered a linear trigonometric equation. It's trigonometric clearly because it contains a trigonometric ratio as part of what you have to try to unwrap to solve for theta, but it's linear because the variable that you're taking the sign of in this case is raised to the 1. Linear expressions have degrees of 1 or powers of 1. If I had something that was sine of theta quantity squared, this is considered to be quadratic as well as trigonometric. And if you take calculus with me, you'll encounter situations where we have a cubic equation. We would have sine of theta quantity cubed. Before I go on though, you need to know something. We do not in mathematics write sine of theta quantity squared. We write sine squared of theta. And that's exactly how it's pronounced. It's sine squared of theta. And it means that you're going to square the sine of theta. Okay, let's take a look at the first example. The first example asks us to solve this trigonometric equation over the domain from 0 to 2 pi. And I'm going to ask everybody to do me a favor here. It's going to make my job explaining this a lot easier. When we rewrite this equation, let's use theta instead of x. All right? I will explain briefly why this is what I want us to do. There's nothing wrong with using x in the equation, but we're going to be referring to the unit circle. And in this equation, we have sine of an angle. And sine of an angle on the unit circle is the y coordinate. So in order for you to find a rotation angle in this question, you're going to be looking at the y coordinate. And that's going to get confusing if you start focusing on the fact that there's an x in the equation. In other words, the x in this equation in both locations is not the same as the x on the unit circle. It's something different. So for that reason, I would like you to change the question to having theta. And if I were to teach this lesson again, that's exactly what I would do. I wouldn't even have x's in there. So this is trigonometric. It contains trigonometric ratios, and it's quadratic. This term, this will become important in a little bit. This term is a quadratic term. This term that's the number 1 is called a constant term. And the sine of theta is a linear term. So I'm pointing this out because how you solve a quadratic equation that contains all 3 types of terms, it follows a certain procedure. And the procedure is that you have to start by zeroing the equation, which means I'm going to set the equation equal to 0 and have 2 sine squared of theta minus 1 sine of theta, you should include the 1 here, minus 1 equals 0, and then we're going to factor this. And this is your first foray into factoring things that are not just x's or y's. Think for a second though, if I had 2a squared minus a minus 1 equals 0. I would like you to pause the video in a second and take what I would say is probably no more time than 60 seconds, literally at this level, to factor 2a squared minus a minus 1. So go ahead and pause the video and do that, and then when you're done, start the video again. Okay, so hopefully what you got is you said that I need a 2a and an a, I need a 1 and a 1, and you figured out that if you put a negative in the second binomial and a positive in the first, and you FOIL that out, you're going to end up with, and I will show this quickly, you're going to get 2a squared, you're going to have minus 2a for your outer, you're going to have plus 1a for your inner, and you're going to have minus 1 for your last, and of course that is what we started off with, 2a squared minus 1a minus 1. And the point I would like to make here, everybody, is that you already know how to factor these expressions. You already know how to factor expressions that are quadratic. And the fact that it contains a squared and a shouldn't change how you factor it, even if, sorry, I'm just catching up to myself here, my computer is going really slow right now, even if it's not a squared and a and 1, but instead it's sine squared and sine and 1. You should still be able to say, you know what, this must be 2 sine of theta and sine of theta. this must be 1 and 1, and then you should be able to reverse engineer the process and decide that I need to put the positives and the negatives in those locations. And if I FOIL this out, then 2 sine theta times sine theta would give me 2 sine squared. 2 sine theta times negative 1 added to 1 times sine theta is going to give me this term of negative sine theta, and then the last two multiplied together will give me the negative 1. This will be maybe the most challenging thing for some of you to grapple with, is how to algebraically work with trigonometric expressions. But I do not want you, we're almost getting ready to solve this. I do not want you doing this all of the time, because starting, well, soon, it will be early next week. No, I'm lying to you. It will be in about a week or so. We're going to be looking at doing a lot of algebra with sines and cosines and tangents and all these other trig ratios. So you cannot rely on changing things to letters like A. Anyway, let's get back to the question now. Just going to get this out of the way. What we have done is change the equation from the top one that you see at the top of the screen here, and we have changed it into two equations that you see below. Now, they're not equations yet, but they're about to be. So remember, when you have a product of two factors equaling 0, each of the two factors can be equal to 0. So we've changed it from a quadratic into two linear, and if we rearrange this equation for sine of theta, we can have sine of theta equals negative 1 over 2, and this equation would be sine of theta equals 1. Now I am going to, wherever possible, rely on the unit circle in order to solve trig equations. So I probably should have said this at the beginning of the lesson, but that's okay. You can pause the video at this point. You need a unit circle in front of you. And you'll probably be happy to hear this since there's no diploma exam. I'm going to tell you that you can always use a unit circle. You don't have to memorize anything. It's going to make our job easier. So pause the video, get a unit circle. I've put a unit circle in the folder that's shared. And we're going to use the unit circle to find out where sine of theta is negative 1/2 and where sine of theta is 1. When you're ready, unpause the video and start playing it again. I'm just going to, on a new page, write sine of theta equals negative 1/2 and sine of theta equals 1. And I'm going to do my best to draw a circle. That's not bad. I have a unit circle, but I'd rather just freehand it. I'm not really happy with that last line. So on the unit circle, sine is equal to negative 1/2. This is negative 1 for y. Remember, on the unit circle, y is equal to sine of theta. So if this is negative 1 at the bottom, negative 1/2 is halfway between that and the origin. We're talking here about this location and this location. Sine is 1 at the top. So you're talking here, everybody, about these three terminal arms. This one, and this one. So what are the angles that give us those locations? Well, the first one at the top is pi over 2. This one here, I'm going to count these off. It's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6. And the last one is 8, 9, 10, 11 pi over 6. Now, those are the solutions between Those are the solutions between 0 and 2 pi. We are also asked for a general solution. And you certainly could write pi over 2 plus multiples of 2 pi, and 7 pi over 6 plus multiples of 2 pi, and 11 pi over 6 plus multiples of 2 pi. But these three positions, you will notice something, they are all separated by the same angle. And rather than writing all three separate plus multiples of 2 pi, what I can do, this is my answer right here for the solution from 0 to 2 pi. My general solution can be written as saying theta is equal to pi over 2 plus multiples of that angle between them. And that angle between them is 1, 2, 3, 4 pi over 6, which is 2 pi over 3. So this is the general solution where you can say n is equal to an integer. By the way, this equation is referred to in math circles as the hippie equation. Because it's the peace symbol. I'm just kidding. It's not referred to in math circles as the hippie equation. Don't tell that to a mathematician. All right, let's take a look at the next question. The next question is also one that we are going to use the unit circle for. I want you to notice in this particular question, though, number 2, that we have secant squared of, let's change it to theta again, and then we have minus 2 is equal to 0. We have a quadratic term, and we have a constant term, but we have no linear term. And when you solve these equations, factoring does not play a role. What you're simply going to do is rearrange for the trigonometric ratio. So we have secant squared of theta equals 2, which means we can take the square root of both sides to get secant of theta equals plus or minus root 2. And secant is the reciprocal of cosine. And that means rather than writing secant equals root 2, we can write cosine equals the reciprocal of the root 2. Now what's interesting here, I find it interesting anyway, what's interesting is you still get two linear equations. You get cosine of theta equals positive 1 over root 2, and you get cosine of theta equals negative 1 over root 2. Now, again, I'm forcing you to use your unit circle here. So let me draw a circle again. Looks like a peach. It's got a little dimple at the top, but that's okay. We are looking for where cosine of theta, which is the x-coordinate, is 1 over root 2, or where cosine of theta is equal to negative 1 over root 2. Remember, cosine of theta is equal to the x-coordinate on the unit circle. Hopefully you remember that the 1 over root 2's are the 45-degree positions in each of the 4 quadrants. So these are the 4 angles. The first angle is 45 degrees. That takes us to here. The second one, which is here, would be 180 minus the 45, which gives us, I want to say, 135 degrees. The next angle, which is here, would be 180 plus 45, which gives me 225 degrees. And the last one would be 360 minus 45, which gives me 315 degrees. So those are the 4 solutions in the domain that we are asked to solve for. I just want to look at the question again. Yep, it said from 0 to 360. In fact, I'm not quite sure why I wrote that twice, but those 2 statements that I've circled mean the exact same thing. Now, it also says what's the general solution. Again, like the previous example, we could, like the previous example, say 45 degrees plus multiples of 360. 135 degrees plus multiple of 360 and on down the line. But what you'll notice, I'll show this to you in a different page. What you'll notice is that when you have that circle and you have those four positions, those four positions are all 45 degrees, my mistake, are all 90 degrees off from each other. So the general solution can simply be written as 45 degrees plus 90 degrees times n, where n is an element of the integer set. So that was example 2. Remember, example 1 had all three types of terms. Example 2 was missing a linear term, and now when we take a look at example 3, it is missing a constant term. And again, we're going to rewrite this with thetas. So we have 3 sine squared of theta equals negative 2 sine of theta. I'm going to add the 2 sine theta to both sides. I guess maybe first I'll make the point that this is quadratic and this term is linear. And how you solve this type of quadratic equation is unique as well. First, you zero the equation. And then you factor. But you don't factor it as binomials. You factor it using a common factor. So we can factor out a sine of theta and be left with 3 sine of theta plus 2. We still have 2 factors. So we can set each of the factors equal to 0. For the first equation of sine of theta equals 0, we can use the concept of the unit circle. Sine of theta is the y-coordinate, so these are the 2 locations. For the second equation, we cannot rely on the unit circle because we don't know where on the unit circle the y-coordinate is negative 2/3. We have to find a reference angle. And we're going to do that by taking the inverse sine of 2/3. Remember that you do not use a negative in your calculator when you go inverse to find a reference angle. And actually, a lot of my work is still up here from the lesson that I already recorded with no audio, but I will show it to you now officially with audio. We go inverse sine of 2/3, and we're going to get 41.8 degrees. I even remember what the angle is. The reference angle is 41.8 degrees. And since the sine of the angle is negative, we're going to construct 2 diagrams. One of them will be in quadrant 3, and one of them will terminate in quadrant 4, because those are the 2 locations where sine is negative. And this is 41.8 degrees, and this is 41.8 degrees. Of course, what we're interested in is not a reference angle. What we're interested in is a rotation angle. So to find each of those rotation angles, in this particular case, we're going to have to take 180 degrees and add 41.8. And in this particular case, we're going to take 360 degrees and subtract 41.8. So let's go back to the diagram on the left. What are our solutions for theta? Well, we can see that it's 0 degrees, and if you look at the top, of this page where the question is 0 is in the domain, 180 degrees, which is in the domain. If we go around and say 360, that would be a solution except for the fact that 360 degrees is not part of the domain. The round brackets mean we cannot include that number. When we take a look at the other two solutions, we need to take 180 plus 41.8, which is 221.8. I'm going to just double check this in a second. And then also we have 360 minus 41.8, which is, I believe, 318.2 degrees. But I'd better check all of those. Would hate to have one of my mistakes on the internet for everybody to see. That's a joke. I don't care what everybody thinks. But let's check it out just for completeness sake. What do we have? 180 plus that angle, which is 221.8. That's good. And then we had 360 minus the 41.8. Yes, 318.2. So those are your four solutions. Now, again, I've given you three examples. They're all different. One has all three types of terms, quadratic, linear, and constant. One has a quadratic and a linear, and one has a quadratic and a constant. They're all quadratic because they all contain quadratic. So you're going to encounter types of those questions in the 8 equations that I would like you trying to figure out until next time, for next time. So on page 212, number 7, and 217, number 21, ask you to solve the equations, and then I believe the terminology is give an exact value if possible, and if not, give a decimal approximation. Well, I'm helping you out here. I'm telling you that on page 212, 7a and 7c, you can use exact solutions, or you're looking for exact solutions. And the exact solutions for page 217 are A and D. Bottom line here is, by the way, everybody, exact solutions mean you can rely on your unit circle. Whereas for decimal approximations, what you're looking at doing is using a concept of a reference angle. So that's it for the day. Again, I'm still a little awkward at this. It's weird. I'm standing in my basement surrounded by stuff, and I have a smartboard on the wall, and I don't see anybody here, and I'm talking to myself. My pacing might be a little off, but remember, you can always pause these videos when you like. Don't forget that tomorrow is a day where the Google Hangouts link will be active. It's probably active now. I just haven't logged into it. And I will put a post in Google Classroom tomorrow reminding you of that and letting you know where we're at so far. So I hope you followed that all right. Remember, if you have any suggestions for how to make these videos better, I would really appreciate hearing them. And in the meantime, it's been good talking to you again. Have a great rest of the day, and we will talk to you tomorrow, hopefully. Good night.